Okay, so I'm going to start our introductions for our first speaker. So we have Oscar Garcia. He has a PhD from Texas A&M in coastal and marine remote sensing, and he's done a lot of work developing algorithms for detection of oil spills from satellite images. A lot of these were adopted by NOAA as a standard method for processing and interpretation of satellite imagery obtained daily. So we're really excited to hear about his talk. He's going to be talking about multispectral UAS mapping for injury assessment of oiled marshes. Are you online, Oscar?
Yes.
Excellent. And then also just wanted to reiterate just a couple of the ground rules as Oscar brings up his presentation. So we do have, just wanted to note that the attendees are muted. However, the chat and question and answer features are enabled. So if you do have any questions, we'd love to hear them, and I'm sure our speakers would be very interested to answer them. And then I guess if you have any event or IT questions, please submit them to the host via chat. And any comments will be also in chat. Okay, and Oscar's talk is going to be 20 minutes long, and then there'll be 5 minutes at the end for question and answers. So Oscar, are you ready? Do you have your presentation up?
Yes.
I don't quite see it yet. Yeah, I think it's just coming up now.
Can you see it now?
Yes.
Good. All right. Well, thank you, Maria. Thanks so much. Thanks, Ellen. Thanks, Jod, and thanks everyone at this workshop. It's always very nice to have this opportunity to share on this workshop the latest and newest of what we've been doing. It's actually, I think this is a good example of how we've been following up this technology. I remember like 3 or 4 workshops ago, we were showing how, which was about 8 years ago, how UAS could be used to detect oil spills. And then we went from there to detect oil thickness. And then from oil thickness, how we went to multispectral, and then from multispectral to real time. I don't know what's next, but it's been a nice trip on this technology. And what I'm going to show you today is a good example of how all that science that has been developed can put together on a practical situation. This is a real life spill that happened in 2018, and we had the opportunity to use this technology. So this is a small spill that have, well, it's not small, it's all relative, right? How much is big, how much is small, but it was a significant amount of oil that was dispersed on the marshes, near the marshes in the Rattlesnake Bay in Louisiana. We were called to respond. We assist there with UAS technology, the UAS that you are seeing here in the center. This drone actually, it was mounted on a crane a few months before at onset, and we were testing precisely this camera here that is on the bottom. It has a multispectral camera. We were testing how we could use a streamline of data coming from these cameras and sensors to characterize oil. So it was a real opportunity to say, okay, so we learned some science, now let's put it in practice. We have a spill, we have to get it done. So, and this spill was very special because not only the amount of oil that we saw on the field, but we had a situation where it was very near a shoreline environment, the marshes, and we have the effects of tides. The tides, this is a very variant environment where tides actually at some point will cover a lot more area with water on the marshes, and then at some point with low tide they will retrieve, and then the more areas get exposed with land. So the timing of the spill was very important because there was so much oil in some areas, unfortunately with very bad timing, because the tide will deposit some of this oil on top of the marshes, as you are seeing here. And then that will make not only the exposure of the shoreline itself, but also some of the oil that will reach inland areas. So that happened in 2018. I presented some of this on the last workshop. And you can see here on the left panel, this was actually a very good opportunity to put in practice the tools that we have developed. It was the first time we used UAS on the field, and we were actually uploading into IRMA on near real-time imagery that we were collecting on the field. I remember my colleagues from NOAA, Ben Shore, Lisa DePinto were there. Also, Dana Tullis from the Coast Guard, we were there on the field, flying the drone, collecting data, uploading data onto IRMA, and then getting the data to actually help us to understand the magnitude of the impact of this spill. So we did that on 2018. We learned a lot. Not everything went perfect, of course. We did very good surveys, not so good surveys, and we had some weather issues, but we did as much as we could. Some of the things that we saw was the potential of the multispectral data to tell us about basically the penetration of that oil reaching higher areas and inland, and this led us to endeavor into another survey in January of 2020, basically repeating the same surveys and see if we could learn, we could detect some changes or the impact of the oil spill. So based on that, I can basically break down the application of multispectral data into these three areas, let's say. So the first one is on your left, oil detection with thickness classification. For sure, we can use UAS to detect oil, where the oil is and how thick it is, that's for sure. Then the other thing is that we learned that by doing multispectral surveys over time, we also then collect data that will allow us to detect vegetation exposure related to the oil, because you see, changes on the healthiness of the vegetation. Also, we detect that after analyzing the data, we saw that we can use this data to quantify the change on land related to the shoreline exposure. So what I have on the screen here is just an example of the data set that we collected on the field. So during the spill, and this, I'm gonna go back and forth, just showing you the classification of the spill. This is an orthomosaic that was made after the data was collected. We create these orthomosaics and we create these maps where we can classify after and get a sense of where the oil was related, and also a reference of how thick the oil was. All right, so the multispectral data. What is the multispectral data? Well, basically, it's sensors that they can actually collect images at a specific wavelengths, all of them separately. For example, here you see we have UV data, we have green data, we have red channel, we have a reddish, which is in between red and near infrared. We also have the near infrared and the RGB. We also have thermal, but in this case, we're not going to be talking about thermal because we didn't use it for this specific study. But these channels that I'm showing you here, just think about a salad, and these are ingredients for a salad. And depending on what you want to achieve, you can just pick and choose these channels and create the products that you want, depending on what you want to study. I mean, you can use particular channels and study soil, or you can use channels to detect oil thickness. But in this case, we were thinking, okay, how can we use these channels to understand the impact on the vegetation of this oil? Well, so there is the development of this concept that is called the Normalized Difference Vegetation Index. This is not something that I came up with. It's a algorithm that has been developed for decades since multispectral data has been available, and it's been used for precisely understand how healthy is a vegetation on an area, and it's based on the near infrared and the red channel. Why? Because, well, so basically the vegetation will show the reflectance associated with chlorophyll and with other concepts related to the humidity inside the plants, basically, and the channels that are going to be more receptive to detect those contrasts are the near infrared and the red channels. Okay, so basically, bottom line is, for these particular applications, we use from these ingredients for the salad, we use the red and the red and the reddish. For example, just before leaving this screen, so if we were looking at about oil detection, I will choose the UV channel, Okay, so and so forth. All right, so in this case, we use the red and the reddish and the near infrared channel. Now, the first challenge that we had to apply these algorithms for the NDVI detection was to georeference the two surveys collected from 2018 and 2020 on the same space, right? Surveying is not as simple as just flying a drone and just collecting data. Unfortunately, if you don't have tools for collecting a very precise survey, like for example ground stations or point of references like structures or things like that, then it becomes challenging to correlate or geo-rectify areas on the same space. So in this case, again, we follow a technique developed by others, which is based on selecting points of reference strategically selected on areas of interest that will help us to align the features over time. For example, in this case, so we select a bunch of points around the islands that we were mapping, and these points were selected over for the two surveys for 2018 that you are seeing here, and for 2020, 2018 and 2020. I don't know what I'm talking. Well then, so since we have the two surveys, 2018 and 2020, and we have the points of reference, we see where those two maps needs to be stretched so they can match the precise space and time. This is important because I mean, anybody that knows a little bit of survey could say, okay, how do you know that you're rectified? Well, we follow this procedure. Well, okay, so now since we have the two surveys well aligned, now we can proceed to do land classification and vegetation classification. So here I'm showing you the two surveys, 2018 and 2020, with the ground points. And before I do any classification, if we look closely, so for example, I don't know if you're seeing my mouse, but what I'm pointing is at the little island that is on the left part of your screen on the upper segment. So you see where the booming was reaching. We have one point of reference outside that booming. So if we look at the island below, you see those points, how the island don't have that land anymore. So, and if you look in every area, almost in every area that you look around these points of reference, you can see the change and without doing any classification. But anyway, so if we look closer, now we are comparing on the same scale. And in this case, in 2018, we used the red line to segmentate the area of land. And in 2020, we used the black shoreline. So right away, I mean, I don't need to explain you anything. Basically, you can see a lot of change from a year, 13 months in difference. For example, let's just look at this island here on the bottom. All this part on the north side of this little island is basically gone. Now, this is 13 months. Erosion is a common factor in this area, and well, it's inconclusive about how much of this erosion was caused by the oil spill itself. But at least we can detect it. We can detect it performing this type of surveys. So one of my colleagues suggested, okay, let's just use a simple quantification method to measure the change. Okay, so then we do a map for one year, a map for the other year, and then we can quantify that in 13 months we had in this particular island, the variation of the land loss was about 13%. Okay, so and so forth. We can do. Okay, well, we found that actually there was a correlation on the loss of land related to how close in relation to the spill site was, which is kind of obvious, but it's nice when data starts making sense, right, with what you are doing. I mean, it's obviously what I'm saying is that the islands that were closer, not only to the source of the spill, but to the location where the spill was, where the oil reached the area, were obviously more affected if they were closer. Okay, so how we quantify change in vegetation? Okay, so we get the NDVI data, we perform gridding, and then for each of the grids, we assign points where we're gonna measure the average, and then all of those points get averaged, and each of these grids are gonna have the average NDVI index for each of the maps. So now we can compare grids to grids, and we can get a quantification of that change on the NDVI. So this is an example, it's an island, and we get the NDVI from 2018 is on the upper panel, and 2020 is on the lower panel. And it's actually, I mean, you see a lot of colors, and yeah, it's somehow difficult to see exactly where is the change. I mean, we can sort of see clearly, I mean, some areas where clearly are different to from one to the other one, but then a good friend of mine suggested me, and this was George Gratinger, who suggested, well, what if we actually map the difference between where is healthier and before than after? So we went back, we took these maps and we subtracted one to the other one, and basically where you have negative indexes because it's basically more stress, and where you have positive indexes because for some reason the areas are healthier than before. And at the beginning, it didn't make sense to me that how could be vegetation healthier, but it was a suggestion from another colleague, Dan suggested, well, I mean, probably vegetation that is relatively more resilient to oil change, to the presence of oil, will take advantage of that other vegetation that is dying and basically extend over the area. So basically this map, and this is just a method that can be repeated over any other area, but here you can see, you can generate a map and see, okay, so these are the areas that got more stress and not so much healthier on this island. But there are some other cases where you can see a lot more change. I mean, that was just an example, but if we look at this one in particular, the entire area is almost completely damaged, and just a very small cluster of vegetation on this little island is healthier than before. But the vast majority of this vegetation on this island basically shows less lower NDVI values. Okay, so this island, which lost 13% of the land, also shows lower NDVI values on 83% of the area. And here we go. So once we have the NDVI, we can actually quantify or measure quantitatively change. I don't see other way to do it with just maps of data. The NDVI requires not only the channels to be acquired, but also the calibration of the reflectances. So I feel like this is a very objective way to use remote sensing to do comparison. You cannot do this class of comparison with RGB, for example. Okay, so conclusions. Multispectral UAS imagery can be used to detect land change, as you saw it before. And I want to point out on the land change, the near infrared channel is the one that shows the highest contrast between land and no land. So I use that channel to actually detect where is the boundary of the land. And using that, well, I was able to compare land change before and after. So we can also detect using UAS, multispectral imagery, we can detect vegetation health, and we can also compare vegetation indexes to evaluate injury. And we also can quantify the impact and injury caused by the presence of oil. And I mean, there is a lot of questions about how conclusive is this? Well, obviously, the more data, the better. This was done with two exercises or two surveys and different times. Obviously, if we could keep monitoring this, we can get more stronger conclusions about if the impact on the vegetation was actually caused by the oil or is just a natural change of the area. one thing we know for sure is that these areas are exposed to a strong erosion situations because of the tide and the currents on the area. So another thing I want to, before I finish, I just want to say, as I was talking to a colleague from Bessie this morning, we were discussing, okay, so 2016, when we were at Onset, we flew a drone and we had a regular camera and infrared. 2018, we had a multispectral camera that just came into the availability of the UAS. And now, I mean, I can tell you so many more, so much newer sensors, better and stronger and more expensive, of course, but I just feel like as we make progress every year on the technology, it's just amazing looking back just 5 years ago, what we were able to do and what we can do now. I feel very, very motivated with this evolution of the technology. So I'm going to stop here and we're just going to leave some time for questions in case there is any.
Thank you so much, Oscar. That was really fascinating. I think we do have some questions.
Yes. Has there been analysis of satellite data to confirm vegetation index trends, or is that data too coarse?
It's a good question. I have not done it. Certainly it's a possibility. And you are absolutely right. It's very coarse, but I think at a certain scale, that can be used. These islands are extremely small, and we rely on the full resolution of the data to use it. But that's always a possibility in a broader scale to use the worldview data to just understand generally. And the good point that you're making is very valuable, because you can do multispectral analysis not only on 2 surveys spread out 13 months, but you can get worldview data every time the satellite passes over. So it's a good point.
Thanks, Oscar. We have a couple more questions. Are the remote sensors used in this project the same as the current Bessie projects? And with your remote sensors and imagery, how accurate can you measure slick thickness?
That's a great question. It's hard to answer in maybe 2 hours, but very quickly. So the sensors, yes, they are the same. Actually, what I was just saying, unfortunately or fortunately, we have new sensors now on the market. I wish I will not be using the same sensors, because the newest sensors you can use on the same camera, better variation, better spread out of the channels, all together on the same lens. What that helps to prevent many problems that we had from the other cameras. But anyway, so answering the question, yes. So they are the same sensors. You can use them for oil spill, for oil thickness detection. What's the accuracy? Well, we have to understand that remote sensing is always good at a given level, and as long as it's not being confirmed with in situ measurements, the accuracy is always going to be questionable, right? So what we have seen is that we can always relate thicknesses from remote sensing within ranges, and we all know the bond agreement ranges, right? So talking about accuracy, well, I mean, we can classify the thicknesses into qualitative classes, like metallic, rainbow sheen, etc. And each of those classes are going to have a range. So there it goes, the accuracy, right? Now, if you have the opportunity to actually take measurements, you can always relate those sensing data to actual measurements. I hope I explained that.
Sounds like it. We have a couple more questions. How do you deal with the tide heights from year to year to outline land masses?
I'm sorry, could you repeat that, please?
Yes. How do you deal with the tide heights from year to year to outline land masses?
No, I have not dealt with that. I'm sorry, but that's a good point. Certainly, I mean, what I'm showing here is just an application and a method. Don't take this as a conclusive data about this specific case. Certainly, what you are saying is a very good point. We have to do an analysis of the intertidal changes to do a more comprehensive analysis of the shoreline change, for sure. That's a very good question. All of them.
Thanks, Oscar. We have one more question. Which program do you use for data treatment?
Well, unfortunately, we haven't found anything out there that fits all our necessities. As we basically, to answer the question, we develop in-house. My wife is a great programmer. I program myself a lot, and we have a couple engineers that help us to customize the programs to basically what we need. So we develop our own software in-house. For example, to do the near real-time data analysis, we've been funded by BESI to actually develop something that we can put out there, and at least the most basic routines that anybody could use are going to be available. Unfortunately, we haven't seen any software on the market that could resolve all the necessities. Pix4D, ArcGIS, ArcGIS, they are all kind of like more focused on land. Once you are on the water, you lose references and it's harder. So that's why we have developed our own algorithms and programs.
Fantastic. Oscar, thank you so much. That was really, really fascinating. And Lindsay, thank you for the questions.